If T was differing, I wouldn't be able to combine the two under one integral. But because T is constant, V is only a function of pressure at that. That's why I can combine them. Okay? If that was at T2 and this was at T1, I wouldn't have been able to combine. So I can combine them, and that's the equation I was after. 1 over RT integral now from P1, T, comma P1, T, comma P2 of VdP. And that is equation 749 of your text. So I'm doing things a little bit out of order, but that's equation 749. Okay? Any questions? All right, now, with that equation now we can easily obtain the alternative definition. So what would be F over F naught? So that would be, using the standard definition, F would be P e to the 1 over RT G minus G ideal gas divided by, at the reference pressure P naught, temperature is the same, e to the 1 over RT. G is going to be at the reference pressure, so I'll put here G naught. And G ideal gas also is not going to be, this is G ideal gas at Tp. This is G ideal gas at Tp naught. So I'll put here G naught ideal gas. Okay? So, doing the same thing with the ratio of expansion that I was doing before, this is equal P over P naught, e to the 1 over RT this minus this, 1 over RT factors, and I have G minus G ideal gas from this guy, minus G reference at P reference minus G ideal gas at P reference. I'm going to break this, combining these two together and combining those two together. So that is equal P over P reference e to the 1 over RT. G minus, this is G at Tp. This is G naught is at Tp naught. That's what the naught means. And then I have minus G ideal gas over G naught minus G naught ideal gas. And let's try to fit it. Can you still read it? Naomi? Okay. So, what's the difference G ideal gas minus G naught ideal gas? Well, we have shown that the difference of G is 1 over RT, this expression here. Well, no, that's the, it was, okay, dG is minus SdT plus VdP. We remember that, right? So, the difference of G, these are at the same temperature. The difference is only in pressure. So G, ideal gas at Tp minus G, ideal gas at Tp naught is going to be the integral of V ideal gas you want TP naught to TP, dP. But V ideal gas is RT over P. RT factors out, RT integral P naught to P dP over P. So that is RT ln P over P naught. Okay. So I have F over F naught is equal E to the 1 over RT G at TP minus G at T. T naught, that's the G naught. Okay. And then I have times E to the 1 over RT times minus RT ln T. Break it like that. You have 1 over RT times RT. There's a minus in front. ln P over P naught. Doing very similar to what I was doing before. The RT cancels. The minus goes in, change it to P naught over P. So this part itself, let me put some color. So this thing here becomes e to the minus ln P over P naught, which is e to the ln P naught over P, and of course that is equal P naught over P. That cancel, okay, so that goes down here. Okay, I forgot the P over P naught over here, that was my problem. There's a P over P naught that I didn't write down. So P over P naught. Like that. The P naught over P cancels this. So the final result is that F over F naught is E to the 1 over RT G at TP minus G standard, which is a P at P naught. What is the definition? The alternate definition? Okay, from here you can take the ln, and you get ln F over F naught equals 1 over RT G minus G naught. In other words, RT ln F over F naught equals G minus G. Okay, so you can get the alternative definitions as a consequence of the Sandler definition. But most texts will have this definition and not the Sandler definition. Any questions? All right. One other thing. We have shown that this is the Sandler definition and recast as the integral involving molar volume. And essentially, what is that? It's V minus V ideal gas, which is RT over V ideal gas, right? It's kind of an obvious expression. But as we know, if we use cubic equations of state, this is not the most convenient form. And we'll be doing a lot with cubic equations of states, specifically Payne-Robinson and SRK are widely used. So instead of this form, you can recast that in the form
Yes, you are on the topic line.
Yes, how to manage that? God, that's bad. Always undisciplined. All right. So you can rewrite this, let me put a big thing here. Rewrite the integral, instead of having v, you have the expression there, and dv here, which is the easier form for dealing with that. Instead of having pressure 0, we go to v becomes infinity. So that becomes integral at t v molar goes to infinity to dv of RT over P, over V, sorry, minus P dV, and then we get a minus ln compressibility factor plus z minus 1. Which is essentially equation 748. So that's the more convenient form for cubic equations to state. We derived this part before, so I'm not going to repeat that. So more convenient. Okay. Next, I guess I'll go a little bit over it. Your text has expressions for the temperature and pressure dependence of fugacity. As you can expect, they're basically recasting of the temperature pressure dependence of J. After a fugacity is a recasting of departure. So I don't want to spend too much time on it. Temperature dependence, it's easier to do ln f so if you start with ln f over p, which is ln f minus ln p, and that is equal, from the definition, 1 over RT integral of v minus RT over p dp, 0 to p. From there, you get that the partial of ln f with respect to pressure at constant temperature, so instead of looking at f, we're looking at ln f as a function of pressure, is equal to the partial of ln p moving into the other side with respect to pressure, which is of course what? 1 over p plus temperature is constant, so I can take 1 over p out, partial with respect to pressure of the integral 0 to p of v minus RT over p dp. Remember calculus. If you have derivative with respect to x of an integral from a finite number, let's say any number a, that's a number, to the variable x, or some function, I don't know, g of tau, d tau. Okay? This is fixed number. Do you remember what that is equal to? G of x. Okay? Calculus maybe 2. So, what is the partial respect to p integral from finite number 0 to p of this? It's going to be the parenthesis. And this is 1 over p. And from here I get plus 1 over RT of v minus RT over p. 1 over p, 1 over RT, RT over p. I hope you can see that this cancels this. So you get v over RT. So that's the temperature dependence of fugacity, the partial of ln f with respect to temperature. Pressure difference, sorry, pressure. I mixed it. With respect to pressure, constant T is equal to V over RT, and that's equation 749. Okay. For temperature dependence, the easiest thing is to do actually fugacity coefficient. So this was pressure dependence. So the temperature dependence partial with respect to temperature of the ln fugacity coefficient at constant pressure. Write it as, since I have ln, is simply the departure Gibbs. Over RT, and since and remember what was the partial of G over RT? We had derived that was H over RT squared.
Oh, I know.
So we have worked with G before. So the result of this is minus 1 over RT squared departure enthalpy. Okay. All right. How we calculate for a gas for which we have a cubic equation of state fugacity, we use this equation plugging in the cubic equation of state for P. And at some point, I will give you what the expression is for specific examples, for example, the Penn-Robinson equation of state.
What are we
But,
What are we calling for RTV?
what do you mean?
If it was a cubic equation, what are we calling for RTV?
We don't pull anything. Constant T, constant R, integral dV over V, changing V. Okay? You can factor out that T and this integral dV over V. Okay. Now,